everybody, it's Mrs. Dinkelman, and we're in the last section in Unit 11. So we've found the interval of convergence, we've found two ways to build polynomials, and now what we want to do is look at what would the error be. So in my mind, here's what pops into my head when we're calculating error. Again, back to the calculator discussion. If in my calculator there's a polynomial that's supposed to represent sine, as a computer scientist, as a programmer, I would have to make sure that when a student looks at those however many decimal places, like 12, I have to make sure that they don't see an error there. Like they have the exact right to 12 decimal places, the like sine of 3, for instance. So for me to guarantee that those 12 decimal places are accurate, I have to calculate what the error might be. That way I know, oh, I need 50 terms for this polynomial, or I need 75 terms for the polynomial, because my calculator can't do an infinite amount of terms. So, or at least some calculators could, but definitely not like a scientific or that kind of thing. So we're going to calculate, there's really two ways to find error, and just kind of a by the way. On traditional, last year was totally different, but on most AP exams, there's always a Taylor or Maclaurin polynomial, usually the very last question, so number 6, and then often the very last like sub question there, so like letter D or letter C is to calculate what the error might be. So there are two kinds of errors. One is for just an regular alternating series, and then the other is really for when you have a Taylor series or a Lagrange. And a lot of times they'll tell you specifically what they want you to do. If you're not sure, but you see that it's alternating, then you can use the alternating, which tends to be the one that's just a little bit easier. So if we have a convergent alternating series, so it satisfies the earlier conditions we talked about alternating series, where the next term is always smaller than the other or the previous one, then we can calculate the error in using just a partial sum. So that means only using a certain amount of terms rather than doing the infinite amount of terms. Then we know that the error is less than the first neglected term. So basically whatever was the first term that you left off, that's going to be our error. So let's talk about where they might ask this. So if they want us to approximate the sum, so we're not finding the exact sum, we're approximating the sum by just using the first 6 terms. So let's see, when n is 1, we're going to have -1 to the 0 over 1 factorial. So our sum is approximately 1 plus, okay, when n is 2, we're going to have a -1 over 2 factorial. When n is 3, it'll be positive over 3 factorial. I'm going to go ahead and put 3 factorial here and show you a trick I don't think I have gotten to really yet. Next one will be -1 over 4 factorial. We're doing 6, so when n is 6, for 6 terms, I guess it's what it says. So 2 more. Okay. So if I wanted to calculate that on my calculator, just here's the quick thing I wanted to show you is that diamond divide, even though it doesn't look like there's anything above there, gets me the factorial. It's like a secret menu. So let's just quickly see what this is. So 1 plus a half minus, nope, 1 minus a half. Plus, I'll just do a 1/6 minus 1 over 4. Again, diamond divide is the factorial. You can also go find it in the catalog or also in the probability section. Usually that's where the factorial is. Okay, hopefully I got them all right in there. And let's diamond enter that real quick. So 0.632 if we're going to round based on our AP calculus rules. Okay, so what we're saying is that's our approximation for the sum of the whole thing, but we know we're off because we've only used 6 terms, so we're off by some amount. And what we're saying is that we think our error then is less than or equal to whatever that last term is. Now, errors generally don't have a positive or negative because we know we could be too big or too little on our error. So our error on this one is just going to be whatever 1 over 7 factorial is. So let's see what that is. And also just a quick quip about error is that generally mathematicians and scientists want to calculate like a really doomsday error, like what's the most I could be off by, because we really want to make sure we know that we're within that interval. So it's kind of the worst possible scenario. Okay, so what we're saying is we're pretty accurate to 3 decimal places. So using 6 terms would be fine if I wanted to make sure I was accurate to 3 decimal places. Okay, so that's the alternating error. Now, what if it's not exactly alternating? I can use, if I've found a Taylor polynomial, I can find that. Now, just a quick by the way, this is still based on that alternating error. You'll notice everything has m plus 1s here. So this should look like the Taylor polynomial. This is how we calculate it. We put some coefficient in front of our n plus 1. So it would still be just whatever that next neglected term would be. The slight difference is this m here. So m is the maximum of the m plus first derivative. Again, we're thinking doomsday, worst possible scenario. So we're going to put the maximum of that m plus first derivative there. So this one is saying, write a third degree Maclaurin polynomial for sine. So I'm going to say, okay, sine is approximately, let's see, it's the odds. So x to the 1 minus x cubed over 3 factorial. Here's where I stop because I got to the third degree, okay? Use that polynomial to approximate sine of 0.1. So sine of 0.1 is approximately, so what I'm going to do on my calculator, 0.1 minus 0.1 cubed over 3 factorial. Okay, let's go do that. So cubed divided by 3, again, diamond divide, and I better do diamond enter. And did it say, didn't say where to round, so I guess we're going to just say 0.1, I guess. Again, if we wanted to keep a little bit more, and I'm going to keep that on my calculator so I can see that. Okay. All right, so how far off might we be? And by the way, this m of 0.1 is just saying plug 0.1 into your Maclaurin polynomial. Okay, so how far off might we be? So I'm going to put m times x minus, we were centered at 0 because this is Maclaurin, n plus 1. So I know that the next term in this polynomial would really be 5, but I stopped with really n was 3. So think back to Taylor, because this is Taylor's theorem. We're going to go one more than that, and then over 4 factorial. So I just kind of like to set it up piece by piece. Well, the x value that we were supposed to plug in was 0.1. So let's see, we're going to have 4 factorial. We're going to have 0.1 minus 0 to the 4th. Now we got to figure out this m. So really what we're trying to find is the 4th derivative of sine, and we want to figure out what its maximum is. Well, the nice thing about sines and cosines is that the derivatives are sines and cosines just with negatives, and the biggest they get, so think about the graph, the tallest they get is 1. Okay, so their m value is always going to be a 1. Okay, so let's calculate what that is. So 0.1 to the 4th, and then divided by 4 factorial. Okay, so 1, 2, 3, 4. We're basically accurate to the 5th decimal place here, which is really interesting. So we could look up here at the 5th decimal place. Now I want to know, because this should be pretty accurate on here, even though it's still technically approximate. I want to know what the actual sign of 0.1 is and see how close. So that one, we must be off somewhere in the 5th decimal place. That brings us up this way. So that's kind of interesting. Anyhow, that's how we calculate the Lagrange error. Again, we will have to do those on the AP exam. I'm almost positive they're going to make us do that. So sometimes, I just want to scroll here because by the way, this on letter C in your homework for, I think it's number 2 here, this is another way that they give that m value. They don't just specifically say it. So this is saying the 5th derivative is less than or equal to 9. Or another way to say that is the most the 5th derivative is, or the maximum that the 5th derivative is 9. So this is really just m. So just be aware that sometimes they will give you that m value. I'm trying to write with my mouse. Anyhow, so get going on try to calculate those errors.